Hello everyone, my name is Xinhang Liu and I am a rising senior from Shanghai Tech University. The topic that I have been focused on during RIS is unsupervised visual to thermal image translation and registration. My mentors are Dr. Huai Yu and Professor Sebastian Scherer at Lab. Visual to infrared image registration is a fundamental problem for high-level tasks such as IR-RGB image fusion, fused object detection, and state estimation. And this task refers to find correspondences between two images pixels. And an important related work is called RIFT, where frequency domain information is used to do feature extraction and matching. The first thing that my mentor Huai asked me to do is to implement RIFT in C++, and the official implementation is in MATLAB, and my implementation is much faster, and the code has been made open source. So think about RIFT. It extracts feature points and then matches them. So we can say this is a sparse approach. And what we want to try is a dense approach, where each pixel in an image is considered and we will look for correspondence in the other image for it. You can view this formulation as finding an optical flow between an RGB image and an IR image. And an intuitive thought about this task is to use image-to-image translation. Here we can see monad to photos translation and zebras to horses translation using an architecture called CycleGAN. And whether we can use simply a CycleGAN to translate an RGB image into thermal. And the answer is no. I have trained a CycleGAN and we translate between RGB and IR images using it. Now we have a pair of RGB and IR images taken synchronously, and we use our trained CycleGAN to translate the RGB into IR and translate the IR into RGB. So if we only look at the results and forget about inputs, these results are reasonable. However, if we compare them with the inputs, you will see some problems. Here, in the translated RGB, it is in the evening, but in the input RGB, it is during the day. So CycleGAN made a naive mistake because it doesn't take advantage of information from the input RGB. So the case for translated IR image is similar. To fix this mistake, we propose an encoder-decoder architecture for RGB IR translation. Here, red arrows stand for auto-encoders for thermal images, and blue arrows stand for RGB auto-encoders, and we can use an encoder to decompose an image into two feature vectors. Here, YA and YB are latent codes for colors of both images, and YC1 and YC2 here are latent codes for geometries of both input images. And recombining these feature vectors can help us translating using both images' complementary information. And here we should also be able to reconstruct two inputs using these latent vectors. So using our encoder-decoder architecture, we can translate the input RGB into an translated IR, where the geometry is aligned with the input RGB, and the color is corresponding to that of the input IR, and vice versa. So now we can do IR-RGB translation well. We can estimate a flow in a single domain or single modality. In addition to our proposed encoder-decoder architecture, we have another way to view these images, which is they can be warped towards each other using an estimated flow. So we use an unsupervised flow estimation module to estimate the flow. Here we show some results of our method. So the flow estimation module and the encoder-decoder kind of benefit from each other. The encoder-decoder can perform image translation and provide a foundation for flow estimation. And the flow estimation module can in turn refine the translated images. That's all for my introduction of my project. Thanks for your attention. I also want to say thank you to Rachel, John, and all the RACE students for helping me, and members at LLab for giving me precious advice.